Alrighty, so today we're going to be having a look at the proof of the power rule, which is we want to show in general how to differentiate, how to derive x to the n. And in the end, we would like to show that this is the rule that we can use. Why? Because if every time we needed to work at f dash of x, we needed to do the limit as h goes to 0 of the difference quotient, we're going to be wasting our time a fair bit. So one of the things we want to be thinking about is how can we speed up this process? And the way we can do it is by proving that there is a way of getting from here straight to here without having to go through all of the business that gets involved in doing that. And so this is going to be a quick proof on why x to the n, the derivative, is n x to the n minus 1. So let's have a look at why. Alrighty, so first of all, let's put in our function. So limit is h goes to 0, x plus h to the n minus x to the n, all over h. Alrighty, and we want to expand out those brackets on the left. How do we do that? That's the challenging. So what exactly is x plus h to the n equal to? Well, let's think about the first term. Well, the first term is going to be x to the n. The second term is going to be x to the n minus 1 h. The next term is going to be x to the n minus 2 h squared, and so on and so forth, by our binomial distribution. Now, we can think about what are the coefficients going to be. Well, we always know that the coefficient of the first one is going to be 1, so we don't have to write that. But what is the coefficient of this term right here? Well, we can work it out by using Pascal's triangle. And in general, if you think about how Pascal's triangle works, is that the first number after 1 is always just equal to n. This is n equals 1, n equals 2, n equals 3, n equals 4, and you notice that the n number is matching these numbers here. So the second number is always going to be n. Whatever n is, that's going to be what our coefficient is, which means that we can put n right here. What's the coefficient here? Well, unfortunately, we're going to have to work that out using a combinations. So we're not going to worry about that term too much, and I'll show you why in a moment. In this case, it's going to be n choose 3. Alrighty. And we're going to get a bunch of these terms until eventually we get h to the n at the very end. Alrighty. So let's substitute that into the top of this fraction over here. So we have an infinite number of numbers potentially on the top, but let's have a look at what happens. Well, first of all, we've got an x to the n and a minus x to the n. So those cancel, and we're left with and what you'll notice is that every single one of these terms has a factor of n, h, on the top. So we can factorize out that factor of h. And you might be worried because you're saying, hey sir, but that doesn't work. We've still got infinite numbers on the top. However, fortunately, a lot of them are going to cancel. Now we're allowed to cancel the h on the top and the bottom, as long as h is not equal to 0. And we're left with this. Now as h approaches 0, the second term is going to go to nothing because it's got a factor of h. The third term, fourth term, and every single other term has a factor of h in it, so they're all going to go to 0, and we are left with nx to the n minus 1, which really tells us the quickest and easiest way to differentiate, which is that if you have any power function x to the n, then that tells us that the derivative of the function is just nx to the n minus 1, which is a very useful rule to have. Alrighty, there's the proof of why the derivative of x to the n is nx to the n minus 1. Next time we're going to be using it.